absolute maximum minimum. F is defined on a set D, so all numbers, contains small c. If f of c, the height is the biggest height out of all other heights f of x, then f of c called absolute maximum. They sometimes call it global maximum. In English, they do not agree actually how to call it. So you will see both, and I'll be using both. Absolute maximum, global extrema, global maximum. Then, if it's the smallest one, guess what happens? It becomes absolute minimum, global minimum. So that kind of makes sense. The most important is to know it's everywhere. Everywhere. To become the biggest maximum, it have to be bigger everywhere. So the absolute extreme value is either absolute max, or you don't have to write down the last sentence. That's absolute extreme value is absolute max or absolute mean. They also called globally. I like globally more than absolute because it means globally everywhere. That is the idea. Now I decided to show you this. I like using this thing in calculus 1 and calculus 3. So this is a 2D object, it's a circle like this. And it becomes a sphere, right? So it's not a sphere right now. Here is the sphere, very beautiful. Then it has, at some point, it has a cylinder inscribed in the sphere, which we're going to learn to find all those volumes in calculus 3, by the way. Also, all of those little things around this vector field has directions and forces, like wind. So that's actually pretty cool. And at some point, when I move it, it becomes a nice, perfect sphere. And then collapses to 2D, right? The idea is, there's a question, what's the biggest size of the cylinder can be inscribed into this? When I move my hands, it becomes a sphere. There's definitely the optimal, that moment when it's the biggest sphere. That's absolute maximum. I wonder how to find that absolute maximum. Not just the absolute volume of the sphere, because it can get smaller, but also angle of my hands. All of this is coming from derivative. How fast does the slinky, which is actually slinky, moving around and making me feel fascinated? That is derivative. How fast is it moving? What direction is it moving? And why this thing exists? Because of the rave culture. Here it is. There's a rave store we have in Tempe downtown, so that's where you can get it. I got it there. And that is my idea. The size of the circle also matters. How come this size was chosen? What radius is the best for the hand to fit any kind of hand size, but not too big, not too small, so you can put it in the pocket. All of these are optimization problems. There's a global maximum of all of those questions, and that's we need to learn how to find global maximum, global minimum too. The question for you, does a function always have absolute extreme values? Do you think all functions have global max, global min? No? Who said no? Yes? What do you think? Up there, yeah? No? Like, if no, then why? Should be, yeah. I feel like everything has max and everything has min. So why do you think it doesn't have? Yeah, yes?
What about a constant?
Constant, very interesting. So constant still works by the definition because it did include. Very good question. So if I have x and y and there's a constant, this is absolute maximum, and this is and distance and distance. They're just all the same because of this equal sign. So greater or equal. Very clever that you asked about that. And we're going to have a function. Actually, now I can ask you, what function has infinitely many absolute maximums and infinitely many absolute minimums? Sine and cosine, check it out. Hill number 1, hill number 2, hill number 3, hill number 4, and so on. And pit, hill. They're all the biggest and they're all the smallest. Thus, these indicated at the top and at the bottom are all global max, global mins. Which function doesn't have it? Like, you don't have to know the name of it. But the idea is, maybe it's not even defined. Not only it may be vertical asymptote and then everything grows forever. The answer is no, exclamation mark. But also, we can have a case when we have holes. Here they are. Draw at least one of those, or both. If there's a hole means the function is not defined there. At 0, f of 0 is not defined. Let me write it down for you. F, it's kind of too thick. F at 0 does not exist or not defined, and that is the one that was the biggest. supposed to be the biggest. So there is no absolute maximum, no absolute minimum, and no absolute maximum at all. If it's defined, then there is max or min. So the second example is better. It has two holes. Basically, what matters is domain. You see this domain? What we're looking at the function 4 minus x squared. That's parabola, concave down parabola, or looking down, right? So parabola looking down has maximum at the top of the hill. But if this top is not included, then there's no absolute maximum. So domain matters. That's my point. Domain matters and shape of the graph matters. Here's the parabola in general. Does it have absolute maximum? Yes. Does it have absolute minimum? No. Again, domain matters. If I have parabola from infinity to minus infinity to infinity, it's going down forever. Same with x cube. X cube looks like a chair, right? But not tangent. From minus infinity to infinity, x cube doesn't have max or min. Absolute. It doesn't have absolute max or min. So it depends on the graph, depends on the domain. That are my 4 examples. Has both if we're restricting at them. You see, and including them. That means both are fine. Has none if we have open parentheses, which means holes. And have some if we have one open parenthesis, but the other one is a closed bracket, and so on. Also, do you have questions before I move on? Is it too fast? Is it boring? Is it okay? Yes? Oh, thank you. It's like, is it boring? He's like, yeah. One more application I like to show. Before COVID, it actually was more interesting. I was working in mathematical modeling of epidemic spreads in my PhD program. So I was modeling MRSA and CD spreads in hospitals and a little bit of malaria. So I knew that before COVID, those ideas were cool to show in class. Now everyone knows too much. So now it's not very interesting anymore. But you see those graphs? Those graphs I copied for COVID cases, number of cases per day. Does it have absolute maximum? The purple color. Yes, here it is. So that is the idea. Absolute maximum means the biggest hill from all the hills possible. This guy also has absolute maximum. Absolute minimum in this case will be 0, 0. So 0 on the floor, basically. And so on. And that means that pandemics or epidemics in general have absolute maximum. They might repeat if we have flu, and for example, we have exactly the same amount of people who got flu this year than last year. That has 2 absolute maximums, and so on. That is the idea. Now, a cool question to you. We learned it before, briefly. When I'm hiking this mountain up, in this case, number of sick people is increasing. What is happening with derivative here? F prime is positive. Whoever thought positive? Yes, that's my point. When you're hiking something up, the slope is increasing. The slope means hike getting harder. It's harder and harder, keep hiking this. Then you reach the top, here it is, and you finally can rest there. That means the floor at the top is flat. That means derivative is 0. And now you're hiking down. When you're hiking down, the slope is negative. The slope derivative is negative. That is the same, works the same with the patients. Number of patients is increasing. That means the function that represents number of patients per time at the hospital, at the country, at the city, whatever, at the ship, at the cruise, is increasing. So derivative of that function is positive. Reach the maximum, finally start decreasing. Maybe medicine was introduced. Maybe everyone got COVID and now there's no COVID to spread around anymore. And so it reached its maximum of population and then start going down. And you know this reduced number of cases happens when people decided to finally quarantine themselves. Because epidemics need to spread. If all of you stay home today, nobody will get sick. If there's epidemic outside of the homes, that makes sense. So the maximum shrinked to a smaller maximum, you see? It shrink down if people or when people stayed at home, got isolated, did not celebrate Halloween in a group of people when you know that everyone is sick. That is the idea. So it has something to do to derivative. That's what we're gonna find out right now. Something to do with derivative. One more question. There will be several questions. Extreme closed interval. Okay, let's write down this theorem first before the next question. If we know that not all functions have maximum minimums, then why even bother finding them? That's a good question. Scientists should not be distracted by finding something for several weeks or months if that doesn't exist. That's why we prove theorems first. That's if you want to know why theorems exist. You're an engineer, you don't care, you just want to build stuff. Not good for you, but at some point you might waste weeks or years of your life on something that doesn't have a solution. And that's happened before to big scientists. So they published books and books. They were number one in the theme, and then the professor, which I was lucky to meet, at some point became so good, he mentioned that none of this exists. The theorem, the math behind it says it diverges, or the solution doesn't exist. And there was a huge bump between two collapsing physics major and math major in those fields. And math major was right. And they have to prove it and claim that all the books had a mistake. So, to prove that it exists, we may mention the closed interval. If a function is continuous, so it doesn't like suddenly disappear, function was behaving nice, disappeared, and then jumped into infinity. No. The function is continuous, no gaps, no breaks, and it is on the closed interval AB. Then absolute max and absolute mean exist. So then we can be bothered to find it. Like in the case with COVID in front of you, it exists. So why would we start looking? Because we know it's there. So let's look for it. Now the next question I wanted to ask, what if, I will use the same purple color, the number of cases of COVID was increasing, reached its maximum, and we already agreed derivative is 0 here. Going down, derivative is negative, decreasing, reached its minimum, and then the second wave started, which unfortunately was the case. So now we have two hills. We agreed that the biggest hill called global or absolute maximum, because by the definition, f of c was bigger than all of f of x, the biggest hill of the hills. But the second hill is also important, so we should kind of mention it. Well, it will be called local maximum. Because locally it's a hill. Locally it is the biggest height, locally. The definition is local min max or local extreme values. Here you go. Let me know if you don't see. Let me zoom in. That's gonna be, I think, the last definition. Local max and min. If C is the same thing as before on the interval, and C is still the biggest out of all f of x, but x is now local and the interval I. So x, so it's going to be locally. Locally has double L? Yes, I think so. Locally, f of c is bigger or equal than f of x. Then it's called local max. And then logically, same thing with local min. If it's locally it's the smallest height. We're talking about height. So if you have lots of hills, they can be all local max means, but one or several can be the biggest ones. Then they will be global ones. And we need to learn how to find those two. What do you think? Yes?
So for the sine function, are they all like global maximums or local maximums?
That's an amazing question. We mentioned sine function. Are they all local or global? What do you think? They're both. So they're global functions and local at the same time. It's not exclusive definition. Yeah, local is part of global if it's the only one. By the definition, locally means over here. Over here, it is the local maximum. But because it's also the biggest one, it's also global. Is it confusing? Or like, it kind of makes sense, but yeah. If all trees have the same height, they're all local and global heights, maximum height, yeah.
So it would be the output?
Output,
when
height.
It's for the extrema, when it's asking for the maximum or the minimum, it's asking for the output.
Yeah, exactly.
Okay.
Oh, we're going to be talking about that too. Good question. When they're asking about max and min value of f, heights, we're talking about heights, f of f. And then where is it happening? That's inputs. So where to look? We don't want to look at infinitely many points. That's crazy. So we're going to look at derivatives. Derivatives. And that's why we're going to have so many cool applications of derivatives that's why we keep pushing you to learn them. Derivatives. Finally, okay, that's the last theorem. Let me check. As always, the beginning of a new chapter has new definitions and theorems. So chapter 4 is amazing. I think you will love chapter 4. Local extreme value theorem. It's also called Fermat theorem. T is silent. Fermat theorem says, if there is a local max-min, it should be the derivative. So if there is any, it should be where derivative is 0 or D and E. Well, let's talk about 0 for now. Yeah, local extreme values. So we don't have to look everywhere. Just find the derivative, find where it hits 0, and that's where your max-min might be. I already showed you on the graph. You agreed with me. Going up, derivative is positive. Going down, derivative is negative. Well, how did it switch the sign from positive to negative? Jumped over it? No. Somewhere it is 0. Makes sense because this is your floor. You reach the top of the hill, you're resting there, watching the sunset. The slope there is 0. So we want to find those zeros, and there they might be derivative. Might not, but might be. So that's the Fermat theorem. That was a big deal to figure that out. So that is a necessary but not sufficient condition. Let me write down this fancy phrase. It is necessary. Can you write down necessary without making a typo? E-C-E-S-S-A-R-R-Y. Necessary. I remember we were learning this word for the GRE and TOEFL exam. Necessary. Necessary but not. And now can you write down sufficient? U-F-F-I-C-I-E-N-T. Necessary means it must be there. Sufficient means not enough. Or sufficient means enough, so not sufficient means enough. So if there is a max, definitely derivative there is 0 or D and E. But doesn't mean that all max and mins. That doesn't mean that where derivatives are zeros, all of those points have max and mins. So there should be more things to check. Local extrema can also occur where F prime, D, and E does not exist. That's what I keep saying. So we're going to be checking both cases. We're going to be checking both cases where derivative is 0 and derivative does not exist. Here's the example in front of you. Absolute value. Absolute value have global minimum. Look at the hike. Imagine you're hiking this graph. Or imagine it's a shape of the roof, so the water goes down, right? So you're hiking it down. First, the derivative is negative. You're hiking up. Derivative is positive. Actually, derivative is positive and always constantly the same. So the slope is always the same. It's 45 degrees all the time, right? So it's pretty cool that derivative is positive, but the same number. Here, derivative should be 0. So what is the problem? Absolute value doesn't have derivatives there. We proved it before using left limit and right limit. F prime at 0 does not exist because of how fast the slope changed. I showed it before. You can check the... so let me write down. But F at 0 is a global mean. Global mean. I showed you with a ruler, or we proved it through the left limit and right limit. This is the slope here, and then slope on the left and slope on the right changed way too fast. So something is happening at 0, and that's something we call cusp, or sharp corner, basically. But it is global minimum. So we might miss those points if we don't check the D and E points. Finally, that's the last definition, at least for today. We're finally going to talk about critical points. And that's the most important. We're going to start to look for critical points. There's already a question on exam 3. Find critical points. Yeah.
So, could we use the same definition to find the local minimum and maximum if we use limits there?
Yeah. Yeah, limits will show you the same thing. It's just harder. Remember, find x squared derivative by limit? It's possible, but longer. So we will be doing rules, but you're right. Everything comes from limits. Critical points.
Can show the theorem,
yeah.
Local extreme value theorem?
Yeah, it is faster to just use rules of differentiation. Oh, you want me to show? I thought you said, is it shorter? CP, I call them CP in this class. Yeah, I'll have all those notes in Canvas. An interior point C of the domain of F. Can you please write this down? A point C in the domain of F. That's going to be important. It have to be in the domain. Where f of f prime at C is 0, or D and E. I'm just going to write down D and E. Called a critical point. So C, interior point C. Critical point is because something critical is happening there. Y derivative is 0. Y derivative does not exist. So something is happening there. Not necessarily min and max. There can be other cases. But still something important. So that's called critical point. American books, again, did not agree on that terminology. You will see in the books in the homework, CP, that's critical point. CN, that's critical number. CV, that's critical value. They mean the same thing, but a little bit off. Sometimes it's x equals something. Sometimes it's x comma y equals something. So I'll be showing you the difference again and again. Just like you mentioned, are they asking about height? Well, they will be asking lots of stuff. So in general, critical value is x equals blah, blah, blah. While critical number or point is a pair. But again, they did not agree on the English terminology of that. So we'll have to just figure out. Well, here's the example when we're going to have zero derivative or derivative of or D and E derivative, but there's no max or min there. Check it out. It's pretty interesting. So going up, derivative is positive. Function is increasing. My pencil is going up. Now, derivative of 0 is 0. Prime is 0 here. Going up, very interesting. So derivative was positive, 0. Derivative is positive again. But there's no max and min there. It's just the intermediate little stop, I guess, of change of height. So derivative is 0, but it's not max and min. Another example is with this kind of cool vertical wall. If it's a hike, then it's pretty cool that you're hiking and you have to have equipment over here. Derivative does not exist here because denominator in the definition of the derivative is 0. Remember, there's a h that goes to 0, and in this case, it's actually 0. So there's no distance between x1 and x2. So you don't have to remember this, but by the definition of the derivative, when you have a vertical wall, the slope is infinite. And it makes sense. If the floor has slope 0, hiking higher, slope is increasing. At some point, the hike becomes very hard. Slope is very, very high. But if it becomes vertical, the slope is called infinite. Yes?
So it's where it goes from curving one direction to curving another direction?
Oh, yeah. We're going to be doing that. Whatever you just mentioned is correct. And we're going to call it first derivative test. Plus and minus, positive direction or negative direction.
And would this be an extrema on the graph of the derivative?
Not on this one, but in the one you mentioned, when it's going one direction and another direction. Oh. Yeah, very good. So that means, make a note. After you copy those graphs or before, I will make a note. CPs, I'll be calling them CPs from now on, so don't be surprised. Critical points are candidates. That's how they call them in English. Candidates for absolute min or max. But they might not be max and min or max. Just like I showed you in the picture right now. Thus, we need to test them. And we're going to learn first derivative test and second derivative test for that. And that's why your exam had second derivative on Monday. And so many of you did not take it. It was kind of very upsetting. That question's supposed to be the good question to get full credit. Everyone took first derivative, and many people did not take the second derivative. It's just not there. And that was upsetting to grade. Yeah. Unfortunately, I was kind of upset about that. I will send you the exams when I finish grading. You can check it out. Finally, let's not blah blah more. Let's practice on the homework examples. How to find critical points for a given function. Let's practice quotient rule also. Don't be scared, don't be scared. Maybe it's not you. Maybe I'm not talking about you. C should not have mentioned. Find the critical points of a function f of x. X over x squared plus 1. It's 5%. That's it. Anyway, what did you just say? Like nothing. How to find critical points? The moment you see the phrase critical points, max min, that should be triggering you to find derivative. So that's one more thing to add to the list. I already made a list for you before. What does it mean to find derivative in your homework or exam? If you want to know fast, especially with English problems, if you have them. If they find how fast, blah, 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 derivative. How fast the balloon is increasing, decreasing. If they ask you, find the rate of change, instantaneous rate of change. What's the slope? Derivative. What's the tangent line? Derivative. One more critical points. Critical points mean they want you to find derivative. Find, let me put capital F. Find derivative of this function. And you need to know that that is indeed quotient rule. U over V. So can you do it faster than me and simplify? This time you have to simplify. It will be important. Derivative of that is x squared plus 1 squared, and don't touch it, leave it as it is. 1 copy x squared plus 1 minus x derivative 2x. Now I want to simplify it, and I'll show you in a second why. When I simplify only the numerator, don't touch the denominator, it's fine. It's already factored, actually, we're lucky. X squared plus 1 minus 2x squared becomes 1 minus x squared. Skip the step, but it's algebra. If you don't believe me, simplify carefully yourself. So put this in the box. That's going to be important to put derivatives in the box. I'm not going to take points off if you don't. Someone asked me about the exam. But for you, visually, that will be important. We're going to have 2 different tests, and it's nice to see which one is which to refer to them later. So this is my derivative. To find critical points, I need to find where this whole thing, the whole thing, is 0, and whereas the whole thing is D and E. Let me write it down.
1 and 5.
F prime is 0. F prime is D and E. You're not supposed to say equals D and E, but does not exist. Where? Solve for x. If this, yes?
There's supposed to be a square on the x on the denominator.
Did I lose a square? Oh yeah, you're right, thank you.
Are we using imaginary numbers yet?
No, not in Calc 1, 2, and 3 actually. They're very protective of students in America, so the imaginary numbers go very late at some point. I don't know why. But maybe because they don't exist. It's a good, you missed a good pun. Because they're imaginary, okay. So, no, not in this class. If it's a fraction, how do we find where this whole fraction is 0? Yes? Correct. But she was quiet, so anyone else? Numerator. More? Numerator is 0. That's correct. Very good job. So for zeros, I will set the top to be 0. How about D and E? Where is the fraction? Does not exist. Yes? The denominator is 0. So I set this bottom part equals to 0. And now I have 2 different equations to solve. I will solve 1 minus x squared to be 0. And I will solve x squared plus 1 squared to be 0. These solutions might be critical points, but maybe not. They must be in a domain. That's a definition which is hard to remember, but they must be in the domain. That will be important at some point. Well, the first one is actually not too bad. X squared is 1, x equals 1. Correct?
Would it be 1 or plus and minus 1?
What do you think? Plus or minus 1. Don't forget, every time you miss a negative answer, a panda is crying somewhere. Plus or minus. Did you see the news that America had to ship all the pandas away to China? Apparently it was a contract for like, whatever, half century, and it was over. And now America had to ship all the pandas. San Diego had the most famous pandas, and all of them are back to China. So, don't make panda crying. Plus or minus 1, don't forget that. 2 points. How about the second one? x squared plus 1 equals to 0 because it's squared. X squared equals minus 1. What's the solution? If I is correct, if there's no I, then no solution. No solution in real numbers. That's how we say it. So no solution in R. If they ask me to expand to C, complex variables, and we expand to C. Okay, do you understand that x squared cannot be negative 1, right? That's just to make sure. So we have x plus and minus 1. Step 2. Let's see. Step 1, we found derivative. Step 2, we checked where derivative is 0 in D and E. Step 3, check if those points you found are in the domain. And we will be giving you examples when it's not going to be in the domain. So you make sure that's important. Are they in a domain? Domain of what? Of original function. Of f. Original function. I'm going to go back and check the original function. The original function is x over x squared plus 1. Minus plus minus 1 and plus 1. Does it make it go away out of the domain? Something bad happens? No. That means it is in a domain. Yes. Check mark. Thus, you can write down, thus, x equals plus or minus 1 are critical points. That's what they can ask you in your homework. And then you will see in your homework, no, they want you to have a pair. A pair means x comma y. That's why they're not supposed to be called points. A point usually is a pair. So that's why sometimes they say, no, it's not a point, it's a value, CV. And don't be bothered by this. I will not be punishing you for like wrong terminology, because to be honest, if books do not agree, why should we agree? I think the most important is to know what is happening than the terminology. This is thus. I'm not sure what it is. Thus. So step 4 is to find the pair. Plug x. Well, let me see. Plug CVs, I guess, into original f of x. And you can even write it down again, or you don't have to. You can just look up. So you found those points, plug them into the original to find the heights. So we found CPs, but those are x's of them. That's location. It's like 1 unit to the north. No, let me see. I guess east is better. 1 unit to the east and 1 unit to the west. But what's the height of it? Let's plug it into the original. F at 1 is 1 over 2. F at minus 1 is minus 1 over 2. Yes or no? I just like carefully. I think it's good, right? Answer. Answer. Critical points. A point usually is a pair. And I'll put it in the purple color. At 1, we have 1/2. At minus 1, we have minus 1/2. And sometimes they ask you to order it from small to big. That's just because of Webwork grading system. That is the final answer. So we learned right now how to find critical points. I gave you the hardest example when we have numerator and denominator. In the future, you'll have all kinds of examples, just the top and just the bottom. In the last 4 minutes, I can show you the graph. Oh, wait. Before we show the graph, what do you think about the process? People who see it for the first time, what do you think about it? Yes? Yeah, no? People who see it for the first time, what do you think about that? Is it doable? Practice. That's a very good comment. You practice a lot, you'll be fine. But knowing how to take derivative, must do. Knowing how to solve equations, full square, blah, 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 factoring, that will be everywhere. But what did we do? I don't understand why we did this. So let me show you. I took this graph and I plotted it in Wolfram Alpha or Desmos or whatever you want. Here it is. Here's the graph of this function. And indeed, at 1 and at minus 1, it has max and mean. Local max, local mean, or maybe even global. That's why we're finding it. Right before we were hiking up and then hiking down after x equals 1. And the height we found That's the height of the hill. And on the left of the -1, we were going down. Down, derivative was negative. Going up, derivative is positive. And at -1, the pit, let's call it a pit, right? Hill and the pit, is -1/2. So that's the whole point here. That's how we will be finding local, global, extreme values. Derivative, find it, set it equal to 0, D and E. Find critical points and then test them. And that's what we're going to learn on Friday. First derivative test, second derivative test, moving on. And it's going to be a very smooth, enjoyable process. You will like it. I dare you not to like it. What do you think about all of this? Questions, critics? Yes?
Can't we just like put the denominator equals to 0 in the original equation instead of the critical points? Like we don't even need to differentiate them.
Come here. I cannot hear you well, so you should come here. Good job, people. Good luck with other exams. I will see you on Friday.
Like the original function.